Okay, so we're still working on related rates, and we're going to look at an airplane problem. And I think the hardest part is figuring out how to draw it and knowing where everything goes. Okay, so we have an airplane traveling horizontally. Okay, so that's important to know that it's not climbing at an angle. Okay, so it's going straight. We've got its altitude, that it's at 3 miles above the ground, and an observer sees the plane flying toward him at an angle of elevation of 60 degrees. Okay, so remember those angles of elevation and angles of depression? So, like if you're a person, let's say you're a person here, and that's your eyesight to the horizontal. If you're looking up at something right there, that is an angle of elevation. Okay? Now, let's say up here is a person, I don't know, maybe they're in an airplane, and they are looking down at that person right there, then that would be your angle of depression. Okay, so if you're looking up, and again, it goes with the horizontal. If you're looking down, and a lot of people put that angle down there, and that is incorrect. Okay, so that angle of depression is up here. Okay, so but in this case, we have an angle of elevation of 60 degrees, and we want to find the rate at which the elevation is changing at that instant. Okay, so the rate, the angle, we're trying to find d theta dt. Okay, so let's make a picture here. So we have an airplane, and it is 3 miles above the ground. Okay, so I'm going to say, here's my airplane right there. It's traveling that way. And then there's a person on the ground. I'm going to put that person over here. And they have an angle of elevation. They're looking up at the airplane. So that angle is at 60 degrees. Okay, and let's see what we know. Okay, so we were told that the airplane's going towards this person. And so this value right here, that's this. So this is actually, this 500 miles per hour is dx dt. Now, think about like the way that I drew it. Based on the way that I drew it, the airplane's getting closer and closer, so this distance is getting smaller and smaller. Okay, so I know that dx dt is negative 500 miles per hour. And the way that you tell that is you got to kind of think, is it getting closer or is it getting farther away? Okay, so what else do we know? Okay, so we have like an X right here, we have a Y, and we have a Z. Okay, so I'm trying to find this guy right here. And I got to look at what do I know. So I don't know anything about that. I know that angle right there. And if I look at y and x, that I could figure out because I have dx dt. So I'm thinking y and x, and this is a constant right here. The plane is always going to be going 3 miles right there, or is always going to be 3 miles above. Okay, so I'm thinking tangent right here. What I'm thinking, that the tangent of theta is opposite over adjacent. Okay, so I can see if I differentiate these, that'll be okay because I know dx dt. So sometimes, you know, I have to fiddle around with them. I try maybe sine and I try maybe cosine, and I realize that I don't have enough information. So that's how I figure out which one of these ratios to use. Okay, so let's see how we can find the tangent of 60 degrees, right? Because that's what we know. So the tangent of 60, because I want to be able to find x right now. Like, how far away is that? Okay, so let's think about our 60-degree angle. Okay, so I'm just thinking in a unit circle that the cosine is 1/2. The sine is the square root of 3 over 2. and the tangent is opposite over adjacent. So opposite over adjacent. And remember that that's just a complex fraction. So it's equal to the square root of 3. So I've got that the square root of 3 is equal to 3 over x. So x radical 3 equals 3. X is 3 over radical 3. And then I'm just going to rationalize the top and the bottom. I would get 3 radical 3 over 3, which is radical 3. Okay, so now I know this distance right here. Okay, so I'm still trying to find the rate at which that is going to change. And again, I don't know anything about this z value over here. Again, make sure if the airplane were like, I think on the homework, the airplane is ascending. In that case, that line would be where the airplane's at. Okay, so I'm still going to go with my tangent, okay, because this is changing right here, and this is changing. These are constantly changing, so those are variables, but that is a constant. Okay, so I'm going to stick with my tangent. So I'm going to say that my tangent of theta, let me go back to that, is y over x. We know that y is always 3, no matter what. Okay, and I'm going to differentiate this, but I'm going to make it a little bit easier and write it like that. Okay, so now derivative of tangent is secant squared. And then derivative of theta is d theta dt. Okay, the derivative over here is negative 3 x to the negative 2 dx dt. Okay, so let's think about what we know about secant squared theta. Well, that's not one that I really have memorized, but I know that it's 1 over cosine squared theta. Okay, let's see. This is going to be negative 3 over x squared dx dt. Okay, it looks like I'm set, but I just need to put in all of my pieces. Okay, the cosine of theta. Remember, theta is 60 degrees. Cosine adjacent over hypotenuse. So the cosine is 1/2. D theta dt, we don't know that. That's what we're looking for. We know that x is the square root of 3, and that dx dt is negative 500. Okay, so this is 1 divided by 1/4. It's just the reciprocal. This is 4. Okay, square root of 3 squared is 3. 3 divided by 3 is 1. A negative 1 times a negative 500 is 500. So d theta dt is 500 divided by 4, which is going to be 125. And we're doing an angle. So angles in calculus, we're always looking at radians. Unless we're specifically told that we're not working in radians, always assume that we're in radians. And we know that we talked about the plane was in miles per hour. So this is radians per hour. Okay.